This is the fourth example in section 12.9, and this example actually comes from UCLA, and it's a bit of a difficult one, a little bit different than what we've done. They're going to give us here x of uv and y of uv. And then let's take a look at our diagram here really quick. So we have our two lines already written in. We also have y equals 8 minus x, and then y equals 4 minus x. Okay, so for part A, what we're looking at is to find the sketch. This one that's given to us is for the XY plane. So we're trying to find the sketch, the domain on the UV plane that maps this particular domain on the XY. So again, we have in the top here, we have the equation for X and then the equation for Y. And so, our strategy basically has been to make a little table here. We have our function of x, y. I'm just calling it f of x. And then the other one is g of uv. So if we start with y equals 8 minus x, and actually maybe this would be a little easier. If we do x plus y equals 8, when we look at the original, the x equation u over v plus 1 and the y, if we were just to combine those, so in other words, if we have x plus y and we are to plug in our u and v equation, we have this, and if we were to combine, because we have the same denominator, we have u plus uv divided by v plus 1, and then we could factor u times v plus 1 divided by v plus 1. So in other words, what happens here is that x plus y is equal to u. That makes this really easy because now this is just u equal to 8. We actually could take the other equation as well, x plus y equal to 4, and that one's just u equals 4. So those two are done. That's pretty straightforward. The other thing that we could notice from the original is that if we look at y, so the equation for y right here, that is actually just x times v. So in other words, y is equal to x times v. Actually, I'll write it as v times x, because then what you'll see is that if we look at the equation y equals 2x, so if we look at y equals 2x, well, if y equals v times x, that means that v would be 2. And if we look at the other one, y equals x, and if y equals v times x, well then v is equal to 1. So there we go. We have our equations that are transferred here, and now we're just going to draw out the UV grid. Doesn't really matter how we draw it out, but let's do v and u like that, and then when we draw in our 4 lines here, we have v from 1 to 2. This isn't going to really be to scale, that's right. And so that's v is 2, v is 1, and then we have u is 4 to 8. Okay, so now again, we're being told to make this transformation, but if we think about this, the reason maybe behind it. So this original region D is very strange looking in terms of any kind of double integral. We would have separated into more than one double integral. Over here, this particular space is really easy because it's just a rectangle, and so we have nice consistent lines. All of our limits are going to be numeric, which is kind of nice, versus this one where all of them are variables. Okay, so then the next step, this was essentially part A right here. The next step for part B is that we're going to take a look at calculating the double integral. So we do need to find the Jacobian now. And Jacobian is going to be a little bit messier than we're used to. In the past problems, it's been a number. In fact, I think both of them were the same. In this case, we have the partial derivative of x with respect to u is 1 over v plus 1. The partial of x with respect to v is negative u over the quantity v plus 1 squared. So that's going to be the power rule. Then we have for y a little bit more complication. Partial with respect to u is pretty easy. That's just v divided by v plus 1. But then the partial of y with respect to v is going to be the quotient rule. So it's going to be the low function multiplied by the derivative of the high minus the high times the derivative of the low divided by the low 1 squared. And we could simplify this, so it doesn't really make sense to simplify these, I guess, but this last one here would be just u divided by the quantity v plus 1 squared. Okay, so then what we get is u divided by v plus 1 cubed minus a negative, so plus uv divided by v plus 1 cubed, and that gives us, now we'll kind of do the same thing as we did up here when we were looking at combining x plus y. So we have u times quantity v plus 1 divided by v plus 1 to the third, and this would then simplify to u divided by v plus 1 squared. And again, this looks very different. This is the Jacobian. Like I said, it doesn't need to be a number like it's been for us in the other examples. This will be a variable Jacobian. Okay, now what we're going to do is we're going to take our double integral, and it is the double integral over d of x plus y, which that part looks pretty simple. However, if you remember, d is a pretty complex region, so that's one of the reasons for using change of variables. And then we're going to transform this or transfer this into a double integral of u and v. What I'm going to do is just use, doesn't matter here, but you could use v on the outside and du on the inside. And then we have x plus y, and I'm going to just do this off to the side. So remember, x plus y was u divided by v plus 1 plus uv divided by v plus 1, and we simplify that down to u. So the integrand is u. The Jacobian that we had found was u divided by the quantity v plus 1 squared, and then the way I wrote it was du dv. And we'll just simplify this one more time here. So we have u squared divided by the quantity v plus 1 squared, and du dv. And then in order to calculate this, it might be easier just to split this up. So 1 to 2 of 1 over v plus 1 squared dv times the integral from 4 to 8 of u squared du. So that's going to give us negative 1 over v plus 1, evaluated from 1 to 2. And then we're going to multiply by 1/3 u cubed from 4 to 8. And I just use a calculator here. So we have 1/6 for that first one times 448 divided by 3. And that simplifies to 448 divided by 18, which we can reduce to 224 over 9. All right, there you go. That's example 4.